exactly 3, then kappa will also be 3, because by assignment 2 you gave a problem.
That's right.
Kappa equal to kappa dash. So if kappa dash equal to 3, then kappa will be 3.
Yes. Yes. That's right. Okay. Yeah, is there any question? Okay. So good morning, everyone. So just a quick recap of the last lecture. We took a 3-connected graph and we observed that we were able to contract an edge, not any edge, but some edge, to preserve the 3-connected property, right? So that's how we went from G to G1, but the edge F1 did not preserve the 3-connected property. We had to choose a particular edge, which was E1 in this case. And if you try further, you will be able to see that in the graph G1, if you contract the edge E2, you will get this graph, which is 3-connected. However, if you contract the edge F2, you will get this graph, which is not 3-connected, because there is a 2-vertex cut that I have shown in the boxes. Okay? So, the theorem of Carson-Thompson that we will try to complete the proof of today says that in any 3-connected graph, so long as you have at least 5 vertices, there is always an edge that you can contract and preserve 3-connectivity. Okay? So this can be viewed as an induction tool for 3-connected graphs, but it's not really a good induction tool unless you can reverse it. So typically, if you want a good induction tool, like ear decompositions for non-separable graphs, you want something that is reversible. So you can also remove ears, but you can also keep adding ears, right? There the reverse is very obvious. Okay? So what we are going to first do is we are going to look at a generation viewpoint of Thomasson's theorem, which is actually easier to prove. And in fact, I will give it to you as a do-it-yourself problem. But I want to first tell you what the generation viewpoint is. Okay? I think someone's mic is on. Maybe it's Kapil. Yeah. Are there any questions or concerns at this point? Okay. So what we want to do is we want to construct a bigger 3-connected graph from a smaller 3-connected graph. Okay? And basically we are going to discuss what is sort of the reverse of contraction, but not exactly. We will have to make it more restricted. Okay? So think about this example. How do you go from this graph back to the original graph G? You take this vertex and you split it into 2 vertices, right? So we are going to call this operation expanding a vertex, but we are going to make it a bit more restricted because we want to preserve 3 connectivity. Okay? So, vertex expansion.
It need not be unique, right?
It won't be unique. Yeah, that's right. That is one key difference between contraction and vertex expansion.
So this is because if we take a vertex and we expand it, then we basically get an edge.
Yeah.
And there will be 2 endpoints of the union between. Now in the original graph G, the neighbors of V, all the neighbors of G may either be neighbors of V1 or V2.
That's right. That's right. Yeah. Okay, so if this is your graph G, then expanding the vertex is basically splitting into 2 vertices, V1 and V2. When you turn on your mic, Aranya, there is a lot of disturbance, so please see if you can fix that. Okay, so we are going to split the vertex into 2 vertices.
Probably my mic.
I don't know whose mic it is, but there is a lot of noise coming.
But I always muted my mic, sir, whenever I do not talk.
No. Right now, when you're speaking, there is a lot of background disturbance. Some kind of background disturbance is coming. So when it is on, I don't mean when it is off.
Okay, but sir, I do not know, sir.
Okay, okay, that's fine. It's not too bad, it's okay.
Okay, okay.
Yeah. So what we are going to do is, we are going to split the edges coming at V. We are going to split them between V1 and V2. Okay? But we need to make sure that the graph is three connected. In particular, each of the vertices V1 and V2 should get at least two neighbors. It doesn't have to be the previous graph. It could be something different. For example, I could do something like this. Okay? So, this is going to be called expanding G at vertex V. So if this is your graph G, then this is the graph H. Okay? So what is this operation? You replace V by two adjacent vertices. V1 and V2, right? So there is an edge between them, they are adjacent. And you distribute all edges incident at the original vertex V in the graph G. You distribute them to V1 and V2. Okay, so every edge that was previously incident at V1 at V is now going to be incident either at V1 or at V2. Okay.
Sir,
Yeah.
what happens to loops?
Good point. Right. So you're saying this situation. So if you just expand
But sir, I have a question. So in the beginning of the discussion of three connected graphs, you said that we are assuming that all graphs are loopless.
that is correct. That is correct. We did assume all graphs are loopless. Right.
Okay.
Yeah. If you do want to consider loops, you can either make it like this or you can make it like this. It won't matter. Okay, but we are assuming that all graphs are loopless. Okay, thanks. Okay, good. And we will ensure that each of the vertex V1 and V2 has at least three neighbors in the final graph H, right? So this three neighbors is including the other vertex V1 or V2, right? So if you look at V1, V1's neighbors are, it includes V2 by definition. Apart from that, it has at least two other neighbors. Okay, so in total, it has to have at least three distinct neighbors because otherwise your graph will not be three connected. Okay, so let me make a slightly more general abstract drawing. If this is your graph G with maybe I'll put a parallel edge here, something like this. Then in the graph H, we'll place it by V1 and V2. And we make sure that at least two of them are neighbors of V1 and at least two of them are neighbors of V2. And the last edge, we can put it anywhere we like. This is the graph H. Okay?
Sir,
Yeah.
I think it will be Vi has at least two neighbors. You have written three.
Yeah, it is at least three.
But sir, here then V2, degree of V2 is 2 in H.
Where? It's not two, it's three. You have to look at the V1 or V2 that it is joined to.
Okay.
Yeah.
So you can say apart from the particular edge V1, V2, every vertex will have at least 2.
That's right. Yeah, but I'm including that edge.
Okay,
Right?
sir.
Okay. So, what is really cool and not so difficult to prove is that if you take a three connected graph G and you take a vertex V of degree 4 or more, so that is another condition we require. Okay, so the degree includes degree is just the number of edges incident at the vertex, right? So it does not mean that the vertex has 4 distinct neighbors. Okay? And if you consider any expansion of the graph G at the vertex V, then the claim is that this graph will also be reconnected. Okay? And the proof, I'm not going to write it, I'm going to just basically give it to you as do it yourself problem. First, notice that if H is a complete graph with multiple edges, so I'll put a star with multiple edges, possibly. Okay, then you're done. Okay, because the original graph is 3 connected, so you're going to get a bigger complete graph. In particular, a 3 connected graph will have at least, let's see, yeah, you want the graph H to have at least 2 distinct neighbors for each of them. So that means that the graph will have at least 4 vertices, right? And all complete graphs on 4 or more vertices are 3 connected. Okay, so you're done. So the only other case is to show that assume H has a pair of non-adjacent vertices. And now you need to show that H cannot have a 2 vertex cut or a 1 vertex cut. Clearly the graph will be connected. If you do this operation, you will not be able to disconnect the graph. That should be fairly easy to see. So all you need to show is that there can't be a cut vertex or a 2 vertex cut. Otherwise the original graph will not be 3 connected. So argue that H does not have a 1 vertex cut or a 2 vertex cut. Okay, that's the proof. All right, so I don't want to spend time on this result, which is quite easy to prove. Okay, good. So it tells you how to make a big 3 connected graph. Right, you start from some graph like K4, and then you keep expanding vertices. There is one problem. If your graph does not have any vertex of degree 4, then what do? Then you cannot make a bigger 3 connected graph from it, right? Because in order to do this operation, you need to have a vertex of degree at least 4. So when you think of the generation viewpoint, it is good to allow another operation, which is adding edges. Because if you add an edge to a 3 connected graph, it will remain 3 connected. That's very easy to see by definition. Okay? So, in order to generate 3 connected graphs, we also allow addition of an edge. It could either be a parallel edge or it could be an edge joining 2 vertices that were not previously connected. Okay? Great. So with these 2 operations, you can keep constructing 3 connected graphs. Right? What is not clear is that all 3 connected graphs can be constructed in this manner. But that will be handled by Thomassen's theorem that we have not proved yet. Okay? You might recall that even in the year yeah, sorry, go ahead.
Sir, I have a question.
Yeah.
Yes, so why we need to have a vertex of degree at least 4 in G?
Well, because of the definition of vertex expansion. Right? Think about this graph. If you have this graph, how will you make a bigger 3 connected graph from this graph?
Okay, sir, I understood. Because if there is no vertex of, so if every vertex has degree at most 3, then after splitting that particular vertex, its endpoints will have degree at most less than 3, strictly less than 3.
Right, exactly.
So that graph cannot be 3 connected.
Exactly.
Okay, sir, got it, sir, got it. Okay. So every vertex must have degree at least 4.
Yes, exactly. Well, there has to be some vertex whose degree is at least 4. Therefore, we are going to allow addition of an edge. Okay?
Sir, also I have a question. So suppose the graph G has a vertex of degree at least 4. So if I take any such vertex and expand it, then the graph will be 3 connected.
Yes, that is what the theorem says.
Okay, okay. Okay, sir, okay, sir.
Yeah? Okay, good. Okay, so in order to construct the graphs, we will allow expansion of a vertex and we will allow adding an edge. Okay. You can do the same in the reverse direction. You can either allow contraction of an edge and you can also allow deletion of an edge so long as your 3 connectivity is preserved, right? But we will prove the stronger statement which says that you don't need to delete edges if you like. You can keep contracting edges. When you get a graph on 4 vertices, then you can delete all the edges and get K4. Okay? Typically, when I apply the theorem, I like to delete all the edges which can be deleted and then do contraction when I am not able to delete any edges, which would be the case in this graph. Because here I cannot delete any edge and preserve 3 connectivity. So I have to use Thomasson's theorem and contract an edge. Okay? Before we prove Thomasson's theorem, I want to state a corollary of these 2 results. Okay? A graph G, and I want you to think about ear decomposition result because this is going to look very similar to that result. A graph G is 3 connected if and only if there exists a sequence of 3 connected graphs G0, G1, G2 up to GR, okay, such that the first graph in the sequence is K4, which is the smallest 3 connected simple graph. The last graph in the sequence is the graph you want, G, and for every intermediate graph Gi plus 1, it is obtained from the previous one, Gi, either by adding an edge or by expanding a vertex at a vertex of degree 4. Degree 4 or more. Right? This is true for all I between 1 and R. Sorry, less than R. Okay, and I want you to think of this in 2 ways. Another way to think about it is the graph Gi is either the next graph, contract an edge, or it is the next graph, delete an edge, right? For some edge E of Gi plus 1. Okay, and why is this corollary true? Well, notice that if you start from some graph G0, K4, and you keep doing addition of edges or expanding vertices, then you will get a 3 connected graph by the previous theorem. Okay, by this theorem and the very easy statement that if G is 3 connected, then G plus another edge E is also 3 connected. Right? So if you add an edge, then clearly the graph will be 3 connected. And by this theorem, if you expand the vertex, the graph will still be 3 connected. Okay? So if you get such a sequence, yeah, go ahead.
Sir, I think that will be easy to see. If G is 3 connected, then G plus will be 3 connected.
That is very easy from the definition. So it's not even.
That's very easy from the definition. Yes, sir. Yes, sir.
Yeah, yeah. Okay. And what is more difficult here is the reverse direction, which is that if you have a 3 connected graph, then you can get such a sequence. But notice that this is implied by Thomassen's theorem, which is slightly stronger. You can always contract an edge and keep the 3 connected property. And when your graph has 4 vertices, it will be K4 with multiple edges. You just throw away the multiple edges, so you delete the edges. Okay? So this will be implied by theorem.
So basically, if we means backward means in this theorem, so if you could indeed prove Carson-Thomassen's theorem, then by that theorem we could say that the forward direction holds. Means if G is 3 connected, then there exists a sequence.
Yes, that's right. Right? So the forward direction is due to Thomassen's theorem, which is significantly more difficult to prove, and the reverse direction is basically do it yourself. It follows from theorem 9.12. Okay? Are there any questions or concerns at this point? Before we proceed to prove Thomassen's theorem, which, as I mentioned in the message, is a fairly sophisticated proof by contradiction. So if there are any questions regarding what the result is saying, this is a good time to ask. Right, so this corollary, as I've stated, it has both the viewpoints. In the reverse direction, is the generation viewpoint. That's how I like to call it. This is the generation viewpoint. And the forward direction, which is more difficult, is the induction, or if you like, the reduction viewpoint, where you take a big graph and you get a smaller graph with the same property, which is 3 connectedness in this particular case. Okay, and when you have both directions, that is generally a very strong induction tool, and it comes in handy to prove various things in graph theory, as you have already seen in the decompositions. Okay, so if there are no questions, then our next goal is to prove Thomassen's theorem. Okay, so for the sake of this discussion, we will say that if G is a 3 connected graph, then an edge E is contractible if G contract E is 3 connected. Otherwise, E is non-contractible. Okay, this is just for the sake of this discussion. These are not standard terms, so if you use them in the assignment, you should also define them. Right? So what is Thomassen's theorem saying? It is saying that any 3 connected graph, so long as it has at least 5 vertices, has a contractible edge. Okay? In order to prove the existence of a contractible edge, it will help us to understand the structure of a non-contractible edge. Okay? So, let us try to understand the structure of a non-contractible edge in a 3 connected graph G. Okay, what I mean is the structure of the graph with respect to this edge. Okay. So let us say G is our 3 connected graph. and E is our non-contractible edge. Okay, and this has at least 5 vertices. What does that mean? That means that G contract E is not 3 connected, right? Well, can it be a complete graph? Anyone? Can G contract E be a complete graph?
No,
No.
because
Yeah, it is not a complete graph. It has a pair of non-adjacent vertices, because otherwise it will be a complete graph with multiple edges, but it has at least 4 vertices, and therefore it cannot be not 3 connected, because all complete graphs with 4 vertices or more are 3 connected. So it has a pair
I mean,
of.
precisely we can say that the underlying simplicity of G contracted E cannot be complete.
That's right. That is exactly what this means, right? It's
Yeah, yeah.
yeah. Right. So it has a pair of non-adjacent vertices. Right. Okay. Good. So how is it not 3 connected? Well, the only way it is not 3 connected is because there is either a 1 vertex cut or a 2 vertex cut. This implies that G contract E, let's call this graph H, has a 1 vertex cut or a 2 vertex cut. Okay? So I will give it to you as a do-it-yourself exercise that the graph cannot have a 1 vertex cut. That is very easy to prove. G does not have a 1
So
vertex.
this is because if H has a 1 vertex cut, then G will have a 2 vertex cut,
That's right. Yeah.
which is
Okay.
contradiction.
So if you have 1 vertex cut in this graph, sorry, by this I mean G, I mean H, sorry. I can write. Because otherwise, when you think about reversing the contraction, you will get a 1 vertex cut or a 2 vertex cut in the original graph G, which is a contradiction. Okay? It's not difficult, so don't worry about this right now. Even if you don't see how to prove this, you will see how to prove this by the end of this discussion. Okay? So the really interesting case is that this graph has a 2 vertex cut. This is the only case that is actually possible. So let's make a drawing. So there is a 2 vertex cut, let's say S, in the graph H. Okay? So after deleting these 2 vertices, you could have a bunch of components. I don't know how many components.
Sir, I think since we know that G contracted E has a non-adjacent pair of vertices,
Yeah.
I think there will exist one such non-adjacent pair which will form a 2 vertex cut.
I don't understand what you're saying, sorry.
Because we know that G contracted E has a pair of non-adjacent vertices. And we will show that G minus C has a 2 vertex cut. So I think that there will be, there will exist 2 vertex cut such that those vertices in the vertex cut, they are non-adjacent in G.
I'm not too sure about that. You can try to prove it, but I am not too confident about that. I don't see why the 2 vertices cannot be adjacent. Okay? But anyways, you might be right. That requires the proof. But we don't need that right now, okay? So let's look at the graph H, which I want to remind you is G contract E. Okay? We have just contracted one edge and we have gotten this graph. Okay? So let's think about contraction of an edge again. If E is your edge UV, what does contracting the edge do? It basically converts this edge into a single vertex, right? Like this. Pushes this edge into a single vertex. So this will be called the contraction vertex. Okay? Let's call this W is the contraction vertex. Let W denote the contraction vertex. Okay? So where is this contraction vertex? Can anybody tell me? Where should this contraction vertex be in the picture?
S.
In S, exactly, you're right. Right, because if the contraction vertex is here, for example, then think about what happens in the original graph. In the original graph, you would basically replace W by the edge E, and all its edges would look like this, which means that S would still be a two vertex cut. Okay, I'm not going to write down that whole argument, but I'll just summarize it. Note that W has to belong to S, otherwise S is a two vertex cut in the original graph G, which is a contradiction because G is 3 connected. Okay, so the only possibility is for this contraction vertex to be inside the set S. In fact, let me change the notation slightly here. Let me call this Z. Okay, let me call this guy W, and this is the contraction vertex Z. Okay, and this is Z. Okay, so the contraction vertex is Z. Okay. Okay, so you have this two vertex cut. It has to contain the contraction vertex, and apart from that, it contains some other vertex W. Is everybody with me right now? Does everybody see why this statement is true? It requires a mild amount of imagination. You have to think about going back from the graph H to the graph G. Okay? So now let's go back to the graph G and see what this looks like. So in G, I can uncontract the edge Z into the original edge E, UV, W, and what will the graph look like? You will still have these components after deleting this set of vertices. Right? This is the original S minus Z plus U plus V. So what have we found in the graph G? In the graph G, we have found that there is a 3 vertex cut, which is not a contradiction because in a 3 connected graph, you could have a 3 vertex cut. But this contraction, this non-contractible edge has to participate in a 3 vertex cut in the graph G. So that is what we have proved so far. Okay. I think I have forgotten the statement of the, okay. So this must be lemma 9.11. If you take a 3 connected graph of order 5 or more, and you take an edge E that is non-contractible, then there exists a vertex W. W is this guy. Let me call E to be UV. Okay. There exists a vertex W such that the ends of the edge E, UV, along with W, is a 3 vertex cut in G. And the proof is what we just did. Okay, that was the proof. Is everybody convinced? Are there any questions or concerns at this point? If anything is not clear, this is the time to ask. Okay, so this lemma is saying that the only reason an edge is not contractible is because the ends of that edge participate in a 3 vertex cut in the graph with some other vertex, right? W. Good. So we are going to use this understanding of non-contractible edges in order to show the existence of a contractible edge. Okay. So now we are going to try to prove Thomasson's theorem, which was, I think, 9.10. Okay. So let's say we have a three-connected graph G. Okay. And let us assume, for the sake of contradiction, that every single edge is non-contractible. Assume that each edge is non-contractible. Okay, we want to arrive at a contradiction. But arriving at a contradiction is not going to be that easy unless we use some more sophisticated ways of thinking about proof by contradiction. Okay. So what we will do is we will choose an edge which maximizes or minimizes a certain quantity. Okay, so the plan is to choose an edge E that maximizes, and this is actually the proof technique I was hoping to see in assignment 1 problem 3, but actually nobody proved it in that technique, but many people gave correct answers. So you can try assignment 1 problem 3 again after seeing this proof and see if you can find a similar argument for that, which I think is simpler than the argument most of you found. So you choose an edge that maximizes or minimizes a certain parameter. Okay? And that will help us in getting at a contradiction. So let's go back to the structure of a non-contractible edge. Okay? So this is what a non-contractible edge looks like. There is a 3-vertex cut with the ends of that edge and some other vertex. Okay? And when you delete these 3 vertices, you will get some components. Okay? So we will get at least 2 components, right? Note that G minus, if I call this S prime, has at least 2 components because it is a 3-vertex cut. It has to have at least 2 components. Right? So what we are going to do is we are going to choose the edge E and the vertex W in such a way that one of these components is as big as possible. Okay? We are going to make it have as many vertices as possible. So we choose an edge E UV and a vertex W such that this is as per lemma 9.11, as per lemma 9.11, such that when you delete the vertices U, V, W, there is a component, let's call this component J, that has as many vertices as possible among all such choices, right? So what are the choices? I want you to think about the choices again. Every edge is non-contractible, so we can choose any edge. And for every edge, there is going to be at least one vertex, W, so that the 3 vertices U, V, W, they form a 3-vertex cut, right? For a particular edge, there might be multiple such choices of W, right? So you consider all these pairs, E comma W, okay? And for all these pairs, you choose one that maximizes the number of vertices in a particular component. So you choose the biggest component and you maximize the number of vertices, okay? So that is what we are doing here. We are maximizing a certain quantity. Is the choice clear? Is it clear what we are doing here? My claim is that, okay, so depends on how you think about it, okay. So now we want to get a contradiction to this choice. We will show that there is some other edge F and some vertex, I think we will call it Y, so that F and Y will contradict the choice of E and W. Okay, so the plan is to find an edge F and vertex Y such that F comma Y contradicts the choice of E comma W. Okay, this is what we have chosen. Okay, so now let's think about this. Let's look at the graph G with respect to the edge E. Okay, so there is a 3 vertex cut, which is the vertex W along with the ends of the edge E, U and V. So we have U, V, W. Okay, let us call this set S. And we have some components after deleting the set S. Okay, think about this component as your component J, which is the biggest component among these 3 components. Okay, there could be 5 components, I don't care. I have just drawn 3 here. Okay, so J is the component of G minus S with maximum number of vertices. Right? If there is a tie, you choose any component you like. Notice that because this is a 3 vertex cut in a 3 connected graph, every vertex in S will have at least one neighbor in all the components. Otherwise, you will get a 2 vertex cut in the graph. Okay, that is not difficult to see. So each of these will have at least one neighbor in every component. Each vertex in S has at least one neighbor in each component of G minus S. Prove this. Okay? Are there any questions at this point? This is a point where we are going to execute our plan. But before we do that, are there any questions regarding the setup? Okay, no questions. Good. So we want to find an edge F here. We want to identify some edge here, F, that will contradict the choice of E. We will worry about the vertex Y later, but let's first focus on the edge. Okay? What are we trying to do? We are trying to make this component, we are trying to find a bigger component with respect to the edge F and the vertex Y. So one way to do this is to basically make the component J bigger by choosing an edge appropriately. So what we will do is we will find an edge that is slightly far away from the component J so that we can just make J bigger and get a contradiction to our choice. Okay, so let's choose an edge like this, which joins the vertex W to a component that is not the component J. Okay, and let's call this vertex X. So what is the plan? Let L denote a component of G minus S distinct from J, so it is not J, and let F equal to Wx denote an edge joining W and a vertex X in this component L. Okay, because of this exercise, there has to be at least some neighbor of W in the component L. This is L. Okay, because every edge is non-contractible, this lemma 9.11 applies to the edge F as well, right? So there is a vertex Y, so that the ends of F and Y is a 3-vertex cut in G. By lemma 9.1, there exists a vertex Y such that the ends of F are W and X. WXY is a 3-vertex cut in the graph G. Okay, let us call this set T. Okay, we have another drawing where we have T. In fact, I won't even make this drawing, it's not necessary. Okay, so let us try to imagine everything here. We are taking the ends of the edge F, W and X. There is another vertex Y. We don't know where that vertex is. It could be anywhere. But these 3 vertices, W, X and Y, they form a 3-vertex cut in the graph G. I want to convince you that after deleting these 3 vertices, there will be a component that will have more vertices than the number of vertices in J. Okay, so the claim is that G delete T, which is WXY, has a component that has more vertices than the original component J in the graph G minus S. Okay? Does everybody agree that if we prove this claim, then the proof is finished? So the only thing remaining is proving this claim. Okay? And I want you all to try it yourself. We will complete the proof of the claim tomorrow. Okay? So this is a good thing to try yourself. It's not too difficult, but it uses things that we have done before. Okay? So the idea is to show that there is a component that is actually a supergraph of J. And in particular, it contains at least one more vertex than J. Okay? So we will do this, we will complete this tomorrow. And that will also give you a chance to go through the whole proof again and make sure that you have understood everything. If you haven't, then we will address it tomorrow first, and then we will complete the rest of the proof. Are there any questions or concerns? Does everybody see why proving this claim proves the statement we are trying to prove?
Yes.
Okay. So the lecture is officially over, but if there are any questions or concerns, please ask. And if not, please feel free to leave. And we will not complete the proof tomorrow, we will complete it on Wednesday. So there is a gap of 1 day. Okay, that's live.
Sir, I have a question. So, will you give a writing exercise after three connected graphs?
That's live.
Okay. So the means writing exercise is basically assignment.
Yeah, but I'm going to allow for the writing exercise students to collaborate and submit one submission per collaboration.
Okay, so is it mandatory to submit to do in collaboration?
It is not mandatory, but I strongly recommend, especially if you are not doing, if anyone is not doing too well in the assignments, I strongly recommend collaboration.
Collaboration, okay.
Yeah.
So basically collaboration in groups of two, right?
Groups of 3 will be allowed, but if you do in groups of 2, that is also okay.
Okay. Maybe groups of at most three.
At most 3. Yeah.
At most three, okay. And so when you submit the writing assignment, that will be single submission for 3 students.
Single submission per group.
Single submission for the group, okay.
Right.
So basically it is group submission rather than individual submission.
That's right. That's right.
Okay. Okay, sir. Okay, sir. And sir, the problems in the writing exercise, will that be from only from three connected graphs?
I'm not sure yet, but it might be.
Okay. And how many problems will be there?
I'm not sure.
Okay.
Sir, will there be a holiday on Friday due to Ganesh Chaturthi?
Oh, I think so. I'll have to check the calendar of IIT-Madras. I will do that after the lecture and send an update to everybody. Thanks for reminding me.
Sir, I have a further question also. Will the difficulty level of the problems in the writing exercise be same as in assignment, or it will be even harder, or?
It will be harder. It will be more than harder, it will be more work. So more than the difficulty level, it will require more case analysis and detailed arguments,
Okay.
which are comparatively lesser on the regular assignments.
Okay. So the amount of effort we put in regular assignments, so there we have to give more effort for the writing exercise.
Yes, definitely. Which is why I'm allowing submission per group, because
Submission
it is
per
too
group.
much work for a single student. So I strongly recommend working in groups.
Okay, sir. Okay, sir. And also we have to submit the writing exercise in LaTeX, right?
Yes, later, yes.
Oh, so basically doing LaTeX is mandatory for the writing assignment. Okay.
Any other questions or concerns? Anything in this proof that is not clear? Did anyone not follow any details that you would like to clarify now? I'm going to stop the recording, but I'm still here for another 5 minutes.